A discrete random variable x takes values 1, 2, 3, 4, and 5, and its distribution is defined as shown. So I'm going to draw it in as a table, which they do below, but I just think it helps here anyway. So when x is equal to 1, we get A. And then when x is 2, when you put 2 in, probability that x is equal to 2 is actually equal to a half times the probability that x equals to 1. And that is carrying on when you put 3 in, the probability that x equals 3 is half the probability that x equals 2. So it's going to be a quarter A, and this follows an eighth A and a 16th A. Now, we know that these must add together to give 1. And just put them into your calculator, 1 plus a half plus a quarter plus an eighth plus a 16th, ignore the A's, just combine the like terms, and it gives 31 over 16. So 31 over 16, lots of A is equal to 1, which means A is 16 over 31. We're there. Okay, so now the distribution is given in full, and yeah, it's all making sense. We've got it halving every time, and we're asked to find the probability that x is odd. And that's going to be the probability that either x is 1, 3, or 5. So we can add these together. To be fair, it's only 1 mark, so you can just write your answer straight down, but here's my work in. I'm going to get 21 over 31. Now, 2 independent values of x are chosen, and their sum s is found. Find the probability that s is odd. So for s to be odd, we're either going to have an odd plus an even for my values of x, or an even plus an odd. Now to get an odd, by the way, do not start thinking, right, 1 and 2 or 1 and 4. Just go for the fact that we found the probability that x is odd. That's what this question is guiding us towards. It's going to be 21 over 31, and then times by the probability of it being even, which is just going to be 1 minus 21 over 31, 10 over 31. So that's going to be the probability of odd and then even. Even and odd is just going to be in reverse, and we can just times by 2. So that works out really nicely. We get 420 over 961. Going to leave it exact. You could write it to 3 significant figures if you prefer. Right, now we're asked to find the probability that s is greater than 8 given that s is odd. Probability s greater than 8 given s odd. Now this is our conditional probability. So the probability of A given B is equal to the probability of A and B over the probability of B. We're essentially reducing the sample space. We're not, instead of dividing through by 1, we're dividing through by probability of B, because we know that not B didn't happen. I'm not going to get into more details in this formula, but you can derive it quite nicely using Venn diagrams. So in our case, it's going to be the probability that s is greater than 8 and s is odd. The only way that could be happening is if s is equal to 9. And then we'll divide by the probability that s odd, which we've worked out before. So getting 9 is going to be 2 over 31 times 1 over 31 to getting 4 and 5. But then we could also get 5 and 4, so I'm going to times it by 2. And then I'm going to divide through by the probability that we found before, which was 420 over 961. If you put that in your calculator, it actually gives 1 over 105. Right, final part of this problem. Sheila sometimes needs several attempts to start her car in the morning, and she models the number of attempts she needs by the discrete random variable defined as shown. Very similar to the one above, but in this case, it's not just from 1 to 5, it's going to go on from forever, actually. Sorry, not x now, we're dealing with y and the probability that capital Y equals y. So, right, now we want to find the probability that y is equal to 1. But what I'm going to call it is b. We used a above, so I'm going to avoid that. But let's use b, and actually our distribution will then be constructed in a similar sort of way. Every time I'm just halving my previous value. So b over 2, b over 4, b over 8, b over 16, but this time it carries on b over 32 and so on. And what we are constructing is a geometric sequence. We're just dividing by 2 every time, but this time it carries on forever. Okay, nice bit of pure creeping in here. So it must be that, again, that the summation of all of these is equal to 1. My first term is b. My common ratio is equal to a half. I don't really want to write down a equals, I will. A equals b. Okay, this is my geometric sequence now. So it must be, remember the sum, this is in the formula book, sum to infinity is a over 1 minus r. So it must be that b over 1 minus a half is equal to 1. And therefore, that ends up being, so 1 minus a half is a half, 2b is equal to 1, so b is equal to a half. And that is my probability that y is equal to 1. Probability y equals 1 is a half. So I would get a half, a quarter, an eighth, a 16th, and so on. Give a reason why one of the variables, x or y, might be more appropriate as a model for the number of attempts that Sheila needs to start her car. The interesting thing about this question is you could choose either one. You just got to give the right reason. So I went with x. I said that x is going to be better. X, more appropriate. Since after 5 attempts, the probability is likely to be 0. In theory, in the other model, you could be trying to start it 20 times and it might start after the 20th. And in reality, I would say that's unlikely. However, you could alternatively say that y is better because y could take all values. In theory, you could start it on the 6th, 7th, 8th attempt, so we should consider that one as well. So as long as you give an appropriate reason for your x or y, then you'll be okay. Okay, good end to this question. Like it overall, actually. Well done.